We are live. So, hello, hackers. See, it doesn't have the same. It doesn't have the same draw, right?
I think you put too much. You're trying to put too much gravitas into it.
It's too much gravitas.
Yeah.
I'm just hello, hackers. How's it going? Well, we'll see. So, today is, I think, January 30th, 2024. We are on week 4 here in CSE598. We have just finished going over microarchitecture exploits for 2 weeks, which was a jolly good time for everyone involved. But this week we are going to move on, and we're going to talk about a topic that is actually quite near and dear to my heart, format strings. So format strings was originally a topic that was discussed in 466 in the undergraduate systems course back when I took it. And then as the course evolved, people were like, format strings aren't that important, you know, when do you really see them? And so they kicked it out. And we didn't even have it on the site for a long time. And so when I had the opportunity to kind of drive the direction of a course, I said, we're bringing format strings back because I thought it was just super cool. And so that's why it's here, because I really like this topic, and I think it's a pretty easy and fun topic to discuss. Give it a moment. OBS is going to work today, which is great. So again, we're kind of on our 3rd module here. This is going to run for 1 week. No surprises here. I think I mentioned in office hours I may be making some changes to the second half. That's still TBD. I'll let you know when I know what I'm doing. Memes. So this wasn't from the class, but it is a totally valid point, and I think it's worth mentioning. During the office hours, there were a couple quotes that could be cited from the original Twitch recording where what I said was factually incorrect. And I am sorry for that. I had it backwards because I took this screenshot, just this snippet of the YouTube video. I didn't play like 5 seconds before, 5 seconds after, and so I was lacking context for what I was describing. And so what I said was objectively wrong, right? And that I realized that is, not what you want from an instructor, right? You want to be told the right thing, not the wrong thing. And some of you may have lost some time due to my error. Now I did dub over it on the YouTube version, so I am stating correct things there. But this meme is calling me out, and I think it's important to acknowledge I'm human, you're human, we all make mistakes, and I'm sorry for that. What I can do, and I think is a fair compromise here, is I will give the entire class 1% course extra credit blanket for this mistake, okay? Because I totally recognize that somebody could have spent that night looking at this and being like, why is this not working? And that's not fair, right? This is a hard course, but I want to be fair to all the students, and so I will add sometime later this evening 1% extra credit to everyone's grade. You'll see it on the grade page, just as a blanket flat thing. And that is something that I will do throughout the course if I do something that is catastrophic, or I add something, add additional challenges, or decide to change something up other than this fixed schedule right here. If I do something that isn't necessarily in your favor, I will try and make it correct from a grading perspective, all right? So, my mistake, but you shouldn't have to pay for it. So everyone will get 1% extra credit. Next meme. So we spent some time on microarchitecture exploitation, and kind of the big takeaway from the pre-recorded lecture videos is just everything's a lie, right? Registers aren't real, instructions aren't real, branching isn't real, right? We're in kind of this mystical land of unicorns, Bigfoot, and fairies. But fortunately, we are going to return to a topic that is much more real with format strings, which is nice. However, CSE365 does have a deadline coming up here on Wednesday, and so I totally expect the dojo to catch fire and not be working, what is that, tomorrow? Yes, tomorrow evening. So even though we are not doing speculative stuff, the dojo will just be on fire. Be aware of that. There's nothing I can do about that. Grades. So this was where we were last week, halfway through on speculative execution. right? So we at the top end, somebody did complete everything in the first half, and the majority of students were about a little bit less than halfway through the module. And we see somewhere ahead of that, somewhere behind of that, more people ahead than behind. If we take a look at where we ended up, it's not this big one here, all right? That I realize the text is quite small. This second one here is speculative execution. And so what we see happened is we still had people at the top end did complete everything, and the top 25% of the class did get, I would guess, I don't know, 82, 85, somewhere around there or better, which is pretty good. Most people in the class scored probably about a 75, right? Which is totally fair, right? We remember that you still get the meme extra credit, you still get the help extra credit, post your memes, post that, cash in, get the extra credit. Because that 75 can easily turn into an A or a B if people were to continue to score 75 across all modules. However, speculative execution is one of the hardest modules in this course. So if you were below this mark, it's okay, right? Format strings is going to be quite easy. It should be, because we're returning to normality here. And so if we take a look at what is going on with format strings, and this is only 4 days in, most students already have completed about 60% of it, right? And so that's a good sign, because we aren't even halfway through this module, and people are more than halfway there. Here is our average. Today, the average is in orange. And so the average person, again, scored right about where I said, probably about a 70, 75 on the microarchitecture module. As far as solve rate, speculative execution was this red here. And we see that there is a nice steady climb, so I don't feel that anyone procrastinated. People spent their time banging their head against this for 2 weeks straight, which is why it ran for 2 weeks. And if we look at format string, some people had worked ahead, clearly. That's why we're starting up a little bit higher. But the initial curve is quite steep as well. That's why we have people that are near 100% there for format strings. Near or at. So that's where grades are. Logistical things. I do have office hours this Friday. I have something that would prevent me from being up at ASU. So I intend on holding them remotely on Twitch. If that's a major issue, let me know. I'll try and work around it, but that is my plan for this Friday. I'm probably not adding any challenges to this module. I know on the Discord I said that I was contemplating adding kind of a boss level. I personally had other things going on, didn't get around to it, so that's not likely to occur. What you see is what you get. If you are interested in solving like a boss level challenge, something that's super difficult, you can check out the Westworld Dojo, which is listed on the dojo here. Down near the bottom. Let me see if I can find it. Right here. This Westworld Dojo with the robot. That includes a couple iterations of what could have been the final boss for this format string module. So if you want something hard to challenge yourself, that is where to look, but it is not going to be required for this course. And that dojo, as well as many of the challenges, were written by not me, but somebody else by the name of Kyle Bott here at ASU in our lab. I do like to try and give credit to those that are the dojo creators. They do get credit at the bottom of the page, but I create some, I don't create them all. Okay, my plans for today, if you have no questions for me. We will return to the comfortable world of IDA, GDB, and things that we can look at and observe. Specifically, we're talking about format strings, so if you have seen the pre-recorded lecture videos, that's awesome. What I am going to talk about today is basically going to be that same concept, just regurgitated live, and we'll see if I do it right or not. One of the things that you can do with format strings is pwn.tools has a format strings function or module. and it can help calculate some numbers that you need in an automatic fashion. However, historically, people hate this tool because they don't understand it, or it's not just a one-liner and then you get the answer, you get the flag. You do have to have a little bit of work, and so we'll take a look at that. And then if I have further time, we'll talk about variadic functions in general. Does anyone know what a variadic function is? The variadic arguments? Sweet. All right. It's at least an interesting topic for the day. All right, let's see if I'm stuck. Tmux. Okay. So I'm on format strings level 1. I don't intend on actually looking at this challenge. Instead, we're going to write something. But that will be a loose approximation. Just for my own knowledge, how many people have seen the pre-recorded lecture videos? Okay. No, and if you haven't, that's fine. Like, do it on your own time. I just want to know so that I know that I'm not repeating myself to the nth degree. So we're going to make a directory called format. I'm going to go here into format, and so I have nothing here. I'm going to include standard io.h. We're going to have a main function. Our main function is going to be pretty boring to begin. Maybe. We're going to call printf. We're going to say %d3. Does anyone know how this function works? This isn't a trick question. If you are aware, yes. Like when this gets called, if I were to compile this, what is this going to look like?
Puts.
It's going to say puts?
Yep.
You sure about that?
Yeah.
Okay. So I don't know if you can see it or not, but that says printf at PLT. So printf is actually the function being called. What I think you were alluding to was if instead of %d, I did something like this. We'll see if I'm wrong here, and that's totally fine if I am. If I pass printf with just a string literal, it will get reduced to puts, which is what we see right here. However, if I use printf and inside this string, I give it this %d and then a second argument, like 3, then it does in fact call printf. Now, the way that this works, if you are not familiar with printf, I actually need to go man3 printf, because the answer is always to look at man pages. And now my terminal has frozen. Sweet. Okay. Fortunately, there is a man page for printf on Mac. Printf and this kind of printf type of function is pretty universal. The way that these work is they take a character string, right, or a character array, character pointer, which is in C, essentially a string, and then what we see here is ... Now, one of the things that I asked is what are variadic arguments or variadic function? All that means, it's a fancy word, is that we don't know how many arguments will be supplied to this, right? It's totally valid. Okay, this is back. It's totally valid for me to say 3, 4, 5, and then supply additional arguments. Right? I get 3, 4, 5. So how does printf know how many arguments should be there? Well, it's looking at this format string that it's provided, right? And so what happens if I don't do this correct as a programmer? Okay? Because if I do %d, and then I still provide 3, 4, 5, what do we think is going to happen? 3, 4?
Does it fail to compile?
Let's find out. So it's not happy, but it's a warning. Warnings are just a suggestion, as I'm known for saying, and it does output, as we would suspect, just 3, 4 here. All right. Now, one of the things that we should have some idea about are function calling conventions. Right? We know the first argument to a function is in RDI, the second argument is in RSI, third argument is RDX, RCX, R8, R9. That's what, 6? Okay. So we said this printf thing can take an arbitrary number of arguments. How many do I have right now? Well, let's change these numbers so that the numbers match their argument. So right now I have 4. And the format string itself is the first argument, right? So that should be an RDI. What happens if I provide 8 arguments? They go into the stack, right? That's absolutely correct. And so if I do this, 1, 2, 3, 4, 5, 6, 7, 8. Actually, I only want 7. Because the format string itself is the first argument. And we run this, we get 2, 3, 4, 5, 6, 7, 8. Then if we look at the disassembly here, what we should see is 7 and 8, right here, are being pushed onto the stack. And so if I were to run this, let's start. Let's disassemble main again. Let's set a breakpoint at main plus 51. So this is right before printf is called. We get to that point, and we look at our display here. We see the arguments of RDI, RSI, RDX, RCX, right? And there would be R8, R9. If we look up here, there's our 5 and 6. And then if we look at the stack here, we see RSP points to 7 and then 8. And so printf has a known way of accessing these values, right? This is a known thing due to calling conventions. A format string exploit is when the attacker has control of this first argument here. We actually don't care about these later arguments, because the argument that is accessed in the format string, or the parameter, right, whether we are accessing RDI, RSI, something on the stack, that is entirely determined by this first argument. So what if instead here we did, what would I want? Let's go buff, have some magic buffer here. We're going to read from standard in into buff up to 256 bytes. If I remember, I don't remember. Yeah, I had it right. We'll include the header file to make the compiler not yell at me. What's up?
It's over the still yell at you because you didn't give enough parameter for printf.
It will probably yell at me. It'll give me a warning, but warnings are suggestions, right?
If you don't include that line, there will be another warning about read, so it's fine.
I don't care about, okay, I want to minimize the warnings, right? I'm not expecting it to be perfect here. Okay, how about this? Okay, assuming I wrote valid C, look at that. No warnings, if I may say so. What we have here is this program will now read from standard in into that buffer that's on the stack. We're going to call printf, where the format string is now controlled by the user. And the first argument, or the second argument to printf, but the first parameter that's going to be considered here is 1. And so now we can have a little bit of fun with this. If I were to run a.out and we give it, I don't know, what do we want to give it? %d, what would we get? 1, right? What happens if I give it %d, %d, %d? It's going to happen.
Leak registers?
What's that?
Will it leak the register?
Yeah, that's exactly what happens. Because what does calling convention say it's going to get these values from? It's going to get it from RSI, which is where we get the 1. Then we get this 256, which is RDX. And we can prove that. We can run this toy example here in GDB. And let's disassemble main. Let's start it. Let's break at main plus 75. So now we need to give it a couple arguments here. And I'm going to do something a little bit different. Instead of D, we'll go %LLX and do that 3 times. Now, because I'm using Jeff, this may eat the output, but here we are right before printf. And once I step to the other side, we should get the output from printf, right? Let's take a look here. What is RSI? RSI is 1, and RDX is hex 100, and then our CX is some stack pointer, right?
I think it's not a...
It's not a stack pointer? I'm a liar? It's totally possible. Okay. So we hit N for next, and what do we see? We see 1, we see 100, and then we see that pointer. And so printf doesn't actually know whether the value that is in that register is supposed to be printed out or not. It just blindly trusts whatever you give it. Okay? And so this has implications.
Blind trust has implications.
Blind trust has implications. Let's see here. What do we got on Twitch? I haven't looked in a little bit. Oh, ye have little faith. Thinking that it will fail to compile. What does UniSTD stand for anyways? I believe it is the Unix standard. But don't quote me on that. That is my own thought, not some knowledge that I have. And yes, somebody else was a believer and recognizes that there were, in fact, no warnings. I appreciate the vote of confidence. So, I said there's implications here. Let's show one of them. We'll have a secret value. Where do we want the secret value to be? No?
598.
598, CSE598. All right, we'll go with that. So now we have this secret value. If you're not familiar with C syntax, what will this line do? Like where are bytes being located? Are things on the stack? Are things in the BSS?
Read-only memory.
Okay, so we have somebody who says it'll be in read-only memory.
It's part of the code, so I think, yeah, would it be the BSS?
Just above, just lower than BSS.
I believe that's what we'll see. But the key thing here is that what is on the stack? Is it the value or is it the bytes CSE598?
It's the pointer, right?
It's the pointer, right. And so we'll have a pointer on the stack to my secret value. Okay. So one of the things that we can see here from man3 printf is there's all sorts of secret codes, like how I used %d and then %LLX. There's a ton of these kind of % codes that you can use. And they all interpret data differently. One of them that is noteworthy here is %s. %s, as you could probably guess, is for strings. It will dereference a pointer on the stack and print the string that is located there. Another thing that you can do is use a $ symbol. And what the $ symbol does is this allows me to access a specific index of these arguments, right? So if I did %D, it's going to show me what is in RSI. That would be the equivalent of doing %$1 If I wanted what is in, this is where I get in trouble and say things that are wrong, because I'm thinking about it off the top of my head. RDX, it should be %$2 right? That would give me what is in RDX. And so we can use this format now. Let's just confirm that. Let's give it $1 We get that first argument, which was the 1, which is what's in RSI. We did that same thing here, $2 go LLX. We get that 100, which is what was in RDX. And we could continue this on through calling conventions until we get to, I believe, 7. And that is the first pointer that is on the stack, if I'm thinking about this correctly.
It should be 6.
You think 6?
Yeah, because the first one is format 3.
RDI, RSI, RDX, or CX, R8, R9, there's 6. And then we drop the 1. So 5 is registers. 6 is the first thing on the stack. Good job, sir. It could be 1. We don't know that it's not. Okay. So let's run the debugger and make sure, right? That.
One thing about your input, you didn't put $3.
Did I do it wrong? $$6 D. Ah, good call, good call. That's how we don't get trapped in rabbit holes. So, there should be, if this from 6 onward is kind of marching up the stack, there should be some number that we could put here that is going to dereference this pointer, right? Because this pointer is on the stack. So RSP plus something will get to this my secret value pointer. So we could, and this is totally valid, except I want to use what? I'm going to use S. Okay, I got a segmentation fault here. Why? What happened?
Dereferencing something that's not.
Right. %S dereferences whatever happened to be on the stack there. I picked some arbitrary garbage, tried to dereference it, and it wasn't correct. And so we could do this, right? And we could do this by hand and play around with it, but we're hopefully a little bit more civilized humans. And we can write something in Python that will do this. So we could say from pwn import star p equals process. Over here we have my generic a.out. I'm going to put this in a for loop for I in range, I don't care, 20. 20 is good. P send. I'm going to use an F string. And what I want is %I $S. And let's give it a new line so that it's a little bit pretty for us. And then let's print P receive all. And I am going to decode Latin 1. Did I get that right? We'll find out. I did. Now, I didn't hide the Pwn Tools help here, and what we see right now is a whole bunch of nulls, but what else do we see here? One of them did in fact access the the pointer to CSE598. And we could, of course, print I to figure out what that is. So it's the 7th index from printf accessed CSE598. Everyone see how we got there? Somebody points out I could do my do.py and then pass it silent, and maybe that would make it happy. So it should be $7 $S, and there's our value. So this means that I can leak values or leak pointers that are on the stack, right? And we could make this number arbitrarily large, right? If I had, instead of main, we took this and we had my func, can I still get to my secret value?
Just go further up the stack, right?
Okay, the statement was yes, just go further up the stack. And that's correct. All right. Hopefully,
You didn't click the function
You
name.
should call the
I should call the function, shouldn't I? Okay. Yeah, whatever. It defaults to something sane. Okay. So, if we run this, it's now blocked on that read. We can Control C. So now we are inside of read, which is called by myfunc, which is called by main. If we go frame 1 and we context, we should be able to say, like, examine, I don't know, what's a reasonable number, 20 strings at RSP? No. 80 strings at RSP. 100 strings at RSP. Well, I'm doing something wrong here, because you can, in fact, do it. Let's finish here, and we'll give it %8 $LLX. Why not? Oh, did it inline? No. Oh, okay, no. I know what I did. Okay. We fini from read. I changed the stack frame to be myfunc and then did fini. And so I finished the frame that I was in, which is why it returned me to main. Okay, so now we're inside of read. I type fini. We give it some value here. Now we're in myfunc. And I should be able to examine like 20 giant hex, RSP. I'm going to venture a wild guess, maybe this one. Nope, that's home hacker. But you see how these values are in fact on the stack. How about this guy? Nope. One of these. We'll just keep grabbing arbitrary pointers and trying to print them out as strings. One of these will in fact point. I promise you, I have missed too many times now, and so now I'll just hang my head in shame. But one of these will in fact point to that CSE598 string value. And so it's just a matter of finding what is the correct offset from RSP to the pointer that we're interested in. And this gets arbitrarily large, right, depending upon what it is we're hunting for. So this shows how we can read a value that's hidden. The other thing that you can do with printf, which doesn't make a whole lot of sense, is you can write with printf. And this goes back to, this is something that isn't in every version of printf. We finally like wisened up a bit and removed it in some instances. But if I find it, there is a character of man3 printf, n. And what n will do, because we love the man pages, it says the number of characters written so far is stored to the integer pointed to by the corresponding argument. So the purpose of this n function is for formatting, kind of alignment, making things pretty. I could have a printf that is going to output some, I don't care, some user provided values, right? But I don't know if this is 1 byte of input or 10 bytes of input, and so I need to know how many bytes were printed to then tab and line things up and make it pretty. And so this n value is here so that you could store the number of bytes written to somewhere in memory to then correct for that later in your code. However, if the attacker controls this buffer, then we could use %n. So let's go back to the original example here where we didn't have my func. GCC do.c. It's still just a warning. No, it is mad because I'm calling my func, which doesn't exist. All right. And we said that I think my secret value is what? %8? %8 $s. No. What was it? 7? Cool. So this is dereferencing that pointer, but I'm claiming that you could also write to that pointer. Now this is a little bit harder to show cleanly in this case. Well, I'll have to use GDB to show you. And the reason for that, and this is a common thing that people kind of get wrong here. If I do like A, so I have 4 A's, and then I do %7 $, let's do HHN. What this will do is it'll say we've already printed 4 bytes so far, because there's 4 A's that are displayed. We're going to take the pointer at the 7th argument to printf, and we are going to write that number, which is 4, and that is what the n does. Right? So if I did this, it would write, I believe, 8 bytes. Right?
Actually, it's 4
Is it 4? Because it's an int.
Yeah.
It's an int, so it'd be 4. Good. See, you know all this already. You're going to crush it. Or are you the one that's already like done with the module? Ha! That makes sense. Let's see. Does printf actually check this writing to an int star? Is the question here on Twitch. Do types exist in assembly? No. Everything is just memory, right? But what the int star indicates, as was mentioned and corrected here, is an int. An int is actually undefined as far as its size, but it is typically 4 bytes in practice. And so it's going to write 4 bytes representing the number 4. Now if I did HN, this H is like half, so it should write 2 bytes. Okay, 2 bytes that will represent the number 4. So we should see a null byte and then a byte with the value of 4. And if I do HHN,
Does that stand for half?
that's what I'm going to go with. Right? Read the man page if you want to know the technical thing, but in my mind, it's half-half. Right? So half-half, and this is going to write a single byte with the value 4. It is not happy at me.
Because it's the read-only memory.
Oh, it came full circle, didn't it? Okay, all right. So let's make it, how do we make it not read-only memory in a trivial fashion?
STRDUP.
What's that?
STRDUP.
Oh, sturdy. No.
Oh, okay. Okay. So if we then like stir copy? I don't know stir dude.
Yeah.
This scares me.
Just copy that string to keep a chunk.
Oh, I don't want to get that fancy.
I think if you do like the array brackets after, like instead of doing a car pointer, doing car array and it's cool, then put it in.
That would put it
parentheses.
on the stack, wouldn't it? Wait. You're saying? No, let's try this. It'll probably be wrong.
That should work.
You're a believer?
No.
Yeah, you sounded confident, and then you came around on me like, maybe not. It didn't blow up, right? Okay. Now it just blows up right away.
Yeah.
Oh, that's because I didn't. Okay.
Just to change strcpy to strdup
The
and
character pointer is
remove
You
the
want-
second parameter 6.
You want this?
Yes.
Except I need to spell right.
strdup, no n, just strdup. It should work.
Okay. Okay. We said 7 was the magic number. I need to give it some A's.
Yeah.
%7, %7, $, HHN. Ooh, it did work. Now I have to remember string dupe exists. Are you a believer? No. Yeah. Twitch enjoyed that interaction, sir. Okay. So my claim here is that we are writing to the first byte of CSE598, but we aren't printing it, right? And what a kind of naive attempt would be is let's do this, and then let's print it out, right? Let's %7 $F. And people would think, oh, now it is doing it? That is not what I expected to happen at all. That ruins the entire premise of something I was going to talk about. What you would think would happen is something like this. I'm going to guess that we...
Because it's in the heap memory, so even there is a snapshot, so
No, so printf, this is a tangent, but why I'm stuck here. Printf, if you use $, does the snapshot, right? And so what you should see here is the C. You should see CSE 598.
But that's on stack. That's not on stack. That's on like heap place because you use the strdup.
Oh, so this magic function you gave me is tricky, right? You're violating the foundational principles of my understanding of printf.
Printf would make a snapshot of stack state because that's about its parameter.
Okay, all right. You know what? I don't want your goofy string dupe anymore, okay? We are done with that. Instead, we're going to say, what do I want? I want to just put these bytes.
You can create a char array.
Ooh, my array. This is what the non-believer was saying, right? You want something like this? You want to just define it as a string?
I think you just do the string. Or you can put it in the brackets.
No, because this itself is a pointer.
My understanding is create a char array and use strcpy. So that's
Right, but you said that that's putting it not on the stack. The point being, see what we've done? We've gone down a rabbit hole of insanity now.
But it's a joint rabbit hole.
I know. Oh, I didn't assign my secret value equals my array. UCC do.c. We run it. We give it the magic value here. %7 $s. This has all gone horribly awry. Okay. Let's find it. Because I changed the stack so it could be at a different location. Now we just don't see it at all. Oh, wait, there it is. 6. AAA percent $6 HHN followed by %6 $S. It's still doing that. Okay. So I can't show you because for whatever reason we don't understand how pointers work today.
Put the string in brackets. I swear that'll work. I promise you.
In curly? You want this?
Yeah, on the other side too. That'll make it just a stack value. It won't make like a constant string. It'll like convert that string to like a hex thing. Like load as a constant.
Yeah, I'm silently kind of rooting against you. But it would get us out of this rabbit hole. Failure. But the point I'm trying to make, which I apparently can't demonstrate, is when you provide one format string to printf, it snapshots the stack, right? And so the thing that we were failing to do is put these bytes on the stack, because a character array is in fact a pointer, and so this is ending up in read-only memory or in the BSS. It's ending up somewhere else that is not the stack, right? And so that isn't getting snapshotted. But in the challenges, and particularly level 3, one of the common things that people get stuck on is the challenge asks you to write to some address. And what people tend to think they need to do is something along these lines, where they need to do %HHN, they need to write some value into memory, and then they need to use that value to then go out and access this. That is not the way you solve the challenge. So don't try and do this type of a thing on level 3, unless we updated the dojo and like have horrifically broken something, which is possible, but I'm not betting against it. All right, I'm not betting that that's what happened. Do not try and do this for level 3, for these early levels, because it doesn't work. Although it's working in our demonstration, because pointers. Okay, so if we ran this with GDB, we see that it's not a C, and we finish from read, we give it %6 $HHN. Then we examine, what do I want? I want this pointer. See, we see right there that pointer is going to that. Examine the string at that. Look, now, so let's have arbitrary like GDB artifact. It is not changed. That is interesting. So like I really think maybe we updated printf and there's like a different behavior than what I'm expecting here.
I think printf is not a clone. Yeah.
Oh, good call, sir. Okay. All right. So now it is doing the thing. It is overwriting that C, which is the first byte of that string pointer, and it has become the byte 4. Right? And so we can use printf to write bytes as well. And that is kind of the nuts and bolts of format strings. That's it. Right? There's a really tricky thing that I talk about at the end of the lecture videos where there's a super magical one-liner that can copy a value from one location to another, but I'm not going to show that because part of the fun of that challenge is figuring out how to craft that, kind of black magic string. And so this module is all about how can we craft these to target specific locations in memory to either leak something or write something, right? Now you do have the expected knowledge of how do I turn an arbitrary write into ROP, right? Or what should I overwrite in memory to gain control of execution? I don't think that is going to be a major challenge. There is one other thing that is mentioned in the descriptions that I think will have to be a surprise. Much like FizzMap was a surprise for some people, there is another surprise in here. Let's see if I can find the challenge. We're overriding global variables. Okay, this one right here. So starting at level 7. Does anyone know what the GOT is? I would expect you to, because you already solved the challenge. Does anyone else? This is all a mystery? That's cool. Global offset table. Okay. So one of the things that we've kind of danced around this entire time when we talk about how functions are called, right? We're just like, yeah, the read at PLT, that's read, right? Forget this PLT thing, just it's read. That's actually not read. If we were to step through that, hopefully that's the first call to read, yes. So, this is a poor example. Does anyone know offhand compiler arguments to do partial railroad? What is it? It's GCC, it's like Z, no railroad. No, there's another.
I don't remember that too.
Disable railroad GCC. I'm not a big, it's WL. No, and then the Z, no railroad. All right. WL comma. I knew like half of it off the top of my head. Okay, that'll work. It's not partial, it's no railroad, but one of the things that is important when we're going to talk about the PLT or GOT is this railroad thing. And we've used checksec before, so we should have an idea of what a stack canary is, we should have an idea of what the non-executable bit is, we should have some idea of what PIE is. I think on the last day of 466 last semester, you guys made me talk a little bit about these, but we aren't going into them. The one thing that we haven't talked about is railroad. Railroad is a protection that prevents what I'm about to show you from being manipulated. And so if you run the challenge for level 7 and you ran checksec on it, you'll see this line here say either no railroad or partial railroad. Okay? If it says full railroad, you cannot do what we're about to discuss. So let's GDB this binary, let's dump out main. I'm going to break right before that read call. It helps if we run. Now, instead of stepping over it, I'm going to step inside. That gets me right to, why didn't that bring me into, okay, no, it is. So we are not at read. We are at read at PLT. And this is an insane thing to step through. And in the 5 minutes that I have, I'm going to do a poor job of explaining it, but I'll hit it again in office hours if you want, because it is kind of interesting. So what happens here is right now, is it PLT? Yeah. There is GLT, PLT, what am I looking for? There is a command that I want that Jeff has. So there is a table, and this is the GOT, and what it is a list of pointers. Okay? When you first start up a program, these functions are in some library, and so they're dynamically linked. Right? And so when the program calls read, it doesn't know where read is. And so there is this setup step that has to occur the first time, and I think since I'm using read, this isn't going to work, but we'll see. The first time a function is called, it has to figure out in real time where is it in memory. And so we go to read at PLT here, and if we step and step, yeah, that's already linked. So I need another, do like exit, right? There's no way this thing calls exit ahead of time. Has no railroad. So I really want partial railroad. Dang it. Okay. But what happens here is I'll have to do it during office hours. Main plus 100. Continue. When you step inside here, this is a kind of a short circuit function where it is going to jump to either the location of exit, or it's going to jump to this kind of like sub procedure where it is going to look up and dynamically figure out where exit is, right? And once that lookup procedure is done, it overwrites the jump pointer to be where exit is, right? So by default, this pointer, this address it's going to jump to, okay, that already jumped to exit instead of where I'm trying to show you. So it will either jump to a setup procedure where it is going to look up where exit is, and then it'll overwrite the jump target to be exit. And the effect of that is you can think of it as a table of pointers. Right? And so when exit at PLT is called, it is going to jump to whatever is pointed at by this address. And that's why I'm saying like this isn't doing the setup ahead of time, because if we look at examine the address that is here, that is what I want. This is that table, that kind of jump logic, where it is going to reference a table to then find the value to fill itself out to then update this pointer. And the thing that we can do is we can overwrite this pointer if railrow is disabled. Okay? And by overwriting that pointer, what happens is when read at PLT is called, it'll jump to wherever we have put that pointer. So
that's GOT. That's
no, it's not PLT? Yeah, how do I get PLT?
You show the assembly code and that's in PLT.
No, but in Jeff, there's like a GLT, PLT. I didn't want to look it up.
PLT, you show that in go up and you can see it.
Okay. Break, star, main, plus 100, run. I don't care. Okay, we are about to call exit at PLT. Oh, I needed to step because I'm goofy. Okay, we are in the PLT.
Yes.
All right, we step, but now I'm in exit.
Because PLT would jump to GOT. GOT is the code that you are, because I think that's full REL.
You think
It's full REL.
full railrow? It isn't though. That's why I'm confused. I would expect to see that if it was full railrow, right? And that's why I'm like, I'm not sure what I did wrong here, because it doesn't have railroad, so that shouldn't be linked already. That should jump into the linking procedure, right? And so I will prep something for office hours, or even post up on the Discord a short snippet so that you can run this and step through this in GDB. But what you will see is that there is a linking procedure that this goes to that will then overwrite a pointer, so that the first time it's called, we have to do this linking work. The second time that it's called, it's just going to reference the pointer itself and jump. So that was a bit of a garbage explanation, and I ran over on time. I will try and hit that again. In this lecture, CSE598 students attempt to shenanigans C. Exactly. All right, does anyone have anything for me right now before I end the stream? 'Cause I'm keeping you late. No? Beautiful. I'm gonna hit the button and the stream, and I will provide an example for this GLT or GOT PLT shenanigans later this evening.